We're still working with radicals today. We're going to look at rationalizing denominators as well as higher powers. So all of the properties we looked at yesterday as well as the definition of radical are the same. In order for a radical expression to be considered in simplest form, there can't be any radicals left in the denominator. In order to rationalize a denominator, you multiply the radical by itself over itself. What we're doing is we're multiplying by a fancy form of 1, because multiplying by 1 doesn't change the value of the expression. It will change what the expression looks like, but remember 2/3 is the same as 4/6. They look different, but they have the same value. One's in simplest form. So that's what we're doing with our radicals. Multiplying straight across, in the numerator we get 3 times the square root of 7. In the denominator, when you square a square root or multiply it by itself, the radical goes away. We end up with 7 in the denominator. Double checking that it's in simplest form. 3 over 7 doesn't simplify any further, so we're done. The next type of rationalizing a denominator is when you have a radical plus or minus something else. It can be a regular number or it could be another radical. In either case, you multiply by what's called the conjugate. The conjugate is when you keep those values the same, you just change the sign. So adding would change to subtracting and vice versa. We'll show you how that works in just a minute. In the numerator, I leave it factored until I'm done seeing what's in the denominator. It's easier to simplify when your fraction is in factored form. I'll distribute later if there's nothing that I can simplify out with the denominator. In the denominator, we need to FOIL 1 times 1. 1 times positive root 6 will cancel with 1 times negative root 6. And then negative root 6 times positive root 6, again, those radicals will cancel. We'll be left with a negative 6. Simplifying my denominator, 1 minus 6 is negative 5. It's also considered poor form to leave a negative in the denominator of a fraction. So I'm going to simplify that negative sign with the 2 in the numerator, and I'm going to distribute a negative 2 to both pieces and drop the negative sign in the denominator. Our next topic is how to evaluate roots other than the square root. Remember, when you evaluate a square root, you're finding what value times itself gives you the radicand, or the number under the radical sign. So to take a cube root, you're trying to find what number times itself 3 times gives you, in this case, negative 8. Now we can't take the square root of a negative number because no number times itself equals a negative. However, when you're multiplying a number by itself 3 times, you can end up with a negative value. We know our root will be negative. A negative times a negative times a negative will give us a negative 8. And 2 times 2 times 2 gives us 8. So the cube root of negative 8 is negative 2. For part B, we're looking for a number that multiplies by itself 4 times to give us negative 64. Same as with square roots, you can't take an even root of a negative number. When you multiply a number by itself 4 times, it will always be positive. So this has no solution. Lastly, we're going to take a look at how to simplify roots that are not square roots. The concept is the same as simplifying square roots, but instead of finding perfect square factors, in, for example, case A, we're looking for perfect fifths. Much easier to do that by factoring than multiplying. So similar to the way that we simplified when we were multiplying radicals, I'm going to simplify the same way with my fifth roots. I'm going to put it all together under one root. 8 is 2 times 2 times 2. 16 is 2 to the 4th power. And x to the 4th times x to the 9th is x to the 13th power. To take the 5th root, we notice that we have 5 2's being multiplied, or 2 to the 5th. The 5th root of 2 to the 5th is 2. I'm going to show you the long way with how to simplify variables first so you understand why this works, and then I'll talk to you about the shortcut. For x to the 13th, we can rewrite it as x to the 5th times x to the 5th, which gives us x to the 10th, and we have x cubed left over. So the same way I took the 5th root of 2 to the 5th, the 5th root of x to the 5th is x, and we have another 5th root of x to the 5th, and that x cubed will be left over with the 2 squared. I had 2 2's left over, multiplied those together to give me 4, and the x cubed was left over from x to the 13th as well. My final step is to multiply those x's together to get x squared. I noticed I dropped the 5th root on the one before. Make sure you don't do that. And we have the 5th root of 4x cubed. As I just demonstrated, it's a very common mistake to drop the index on roots because we're so used to square roots that we don't write a number there very often. So be sure to keep that index as you are working. It's important to keep track of that. Math is a very precise language, and we want to make sure that all of our steps are reflecting equality. Part B, I'm going to start by dividing just like I did with square roots. 486 divided by 3 is 162. Bringing that negative up to the numerator to make it positive, I will add my powers to get a total of 34. Breaking 162 down into primes, I'll show my factor tree off to the left here. 162 is 81 times 2. 81 is 9 times 9. And 9, of course, is 3 times 3. So we have 3 to the 4th power times 2 to get 162. With our variables, we could break this up into x to the 4th times x to the 4th over and over until we get something left over like we did with our number. But the easier way is to find a power that is a multiple of 4 and then multiply by whatever's left over. Remember, our power rules, when we multiply powers, we add the exponents. So x to the 32 times x squared does equal x to the 34th power. To take the 4th root of x to the 32, you divide 32 by 4. Starting off with 3 to the 4th, the 4th root of 3 to the 4th is 3. That 2 will be left over. The 4th root of x to the 32nd power becomes x to the 8th because 32 divided by 4 is 8. We saw something similar on part A when we did break it up. We had 2 groups of x to the 5th, and 13 divided by 5 is 2 with a remainder of 3. The leftovers stay under the 4th root, and we had 2x squared left over. Part C, we are trying to add roots. Remember, they must be exactly the same under the radical in order to be able to combine them. Starting by simplifying, we need to find perfect cubes as a factor of 40. 40 is 4 times 10. 4 is 2 times 2. 10 is 2 times 5. So we have a perfect cube factor of 40, 2 cubed. For 135, 5 is a factor of 135 times 27. 27 is 9 times 3, and 9 is 3 times 3. So we have another perfect cube factor of 135. Working down the page here, we're going to keep that 2x that is on the outside of our radical. Here we have a 2 cubed. The cube root of 2 cubed is 2. With x to the 4th, we have x cubed times x. So the cube root of x cubed is x. Our leftover values are 5 and x. The second piece is a little bit trickier. We have a negative sign under the cube root. Remember when we evaluated the cube root of -8, our answer was negative. We can think of this as also having a factor of -1. The cube root of -1 is -1 times 3, the cube root of 3 cubed, with x to the 7th, this would be x to the 6th times x. The cube root of x to the 6th is x squared. I simply divided the 6 by 3, the root. And then what we have left over is a 5x under the radical. Cleaning this up a little bit by multiplying our coefficients, 2x times 2x is 4x squared times the cube root of 5x minus 3x squared times the cube root of 5x. In this case, with variables on the inside and outside of our radical, we have to make sure we have like terms in both places. Outside, those coefficients are both x squared terms, and under the radical, they're both 5x. So we do have like terms. We'll take 4x squared minus 3x squared, which leaves us with 1x squared, times the cube root of 5x. Here are 3 U-try problems. None of them are as complex as that last one. If you had trouble following any of that, we'll start with questions in class.